Lecture 113. Physics of Musical Instruments. Sound of a strange, ethereal instrument plays. Welcome to the hidden realm where physics and music intertwine, a world where mathematical precision gives birth to sublime beauty. I'm Professor, and today we venture into the enigmatic domain of musical instruments and the mysterious forces that allow them to enchant our senses. What invisible energies are unleashed when a violinist draws a bow across strings? What arcane principles govern the transformation of breath into melody? Today, we'll unveil these secrets. Consider this: every note that has ever moved you to tears, every melody that has stirred your soul, emerges from nothing more than disturbed air molecules, vibrations that travel in patterns so precise they seem almost supernatural in their perfection. Yet behind this apparent magic lies a realm of scientific principles so elegant that the boundary between physics and artistry blurs into insignificance. The instruments we cherish are not merely objects. They are physical embodiments of mathematical relationships, acoustic phenomena, and resonant mysteries. Today we'll decode these sonic enigmas, peering into the very soul of music itself. Before we dissect specific instruments, we must first understand the fundamental nature of sound itself, the invisible messenger that connects instrument to ear, performer to listener. Sound is, at its essence, a disturbance, a pressure wave propagating through a medium, typically air. When an object vibrates, it compresses and rarefies the air molecules around it, creating regions of higher and lower pressure that travel outward like ripples on a pond. But what transforms mere noise into music? The answer lies in the patterns of these vibrations. When vibrations occur in regular, periodic patterns, our brains interpret them as musical tones. The frequency of vibration, measured in hertz, determines the pitch we perceive. Higher frequencies yield higher pitches, lower frequencies produce deeper tones. What's particularly baffling is how our perception of music arises from mathematical relationships between these frequencies. The ratio 2:1 creates an octave, a relationship so fundamental that cultures worldwide recognize it despite having no contact with one another. A 3:2 ratio produces a perfect fifth, the interval that opens, "Twinkle, Twinkle, Little Star." These aren't arbitrary preferences, but rather reflections of how our auditory system processes vibrational patterns. The mathematics of music seems woven into the very fabric of our perception, a tantalizing mystery at the intersection of physics, biology, and psychology. Behind each musical note lies not just a frequency, but an entire spectrum of overtones, additional frequencies that color the sound and give each instrument its distinctive voice. Now, let's delve into the realm of resonance, one of the most captivating phenomena in all of physics. Resonance occurs when an object is subjected to vibrations matching its natural frequency, causing it to vibrate with increased amplitude. This principle is the hidden force behind all musical instruments. Each instrument contains resonant structures, the body of a violin, the tube of a flute, the membrane of a drum, that amplify certain frequencies while dampening others, sculpting raw vibration into musical tone. Standing waves emerge when waves bounce back and forth within a confined space, creating patterns of motion where some points remain stationary, nodes, while others vibrate with maximum amplitude, antinodes. These patterns, invisible to the naked eye yet fundamental to all music, dictate which frequencies an instrument can produce. Let us begin our journey through instrument families with string instruments, perhaps the most mathematically elegant of all musical contraptions. When a string is plucked, struck, or bowed, it vibrates according to principles first articulated by Pythagoras over 2 millennia ago. The pitch of a vibrating string depends on 4 factors: its length, tension, mass per unit length, and stiffness. Shorter, tighter, thinner strings produce higher pitches, a relationship we can express precisely through the wave equation. But the true enchantment of string instruments lies in their harmonic structure. A vibrating string doesn't just move as a whole, it simultaneously vibrates in halves, thirds, quarters, and so on, each producing a frequency that's a multiple of the fundamental. These overtones aren't just mathematical curiosities, they give string instruments their rich, complex voices. Consider the haunting mystery of Stradivarius violins. despite centuries of examination, the precise reason for their superior sound remains elusive. Is it the wood, the varnish, the geometry? Modern science has employed CT scans, material analysis, and acoustic mapping, yet still, these instruments guard some of their secrets. One of the most bewitching phenomena in string physics is sympathetic resonance, where strings vibrate spontaneously in response to other strings being played. In instruments like the Hardanger fiddle or sitar, additional strings resonate without being touched, creating an ethereal halo of sound that seems to defy explanation. This ghostly response gives these instruments their distinctive shimmer, a physical manifestation of invisible connections. The piano presents another acoustic wonder. Its strings are purposely tuned, slightly imperfectly. This intentional mistuning, called inharmonicity, creates a stretching of higher octaves that matches our perceptual expectations better than mathematically perfect tuning would. The piano is thus designed around a beautiful deception, a compromise between physical ideals and perceptual reality. Wind instruments transport us to a different realm of physical principles. Here, the vibrating medium is a column of air rather than a string. When a musician blows into a wind instrument, they create a pressure disturbance that resonates within the air column. The mathematics of air columns differs fundamentally based on whether the pipe is open or closed at one end. In open pipes, like flutes, all harmonics are present. In closed pipes, like clarinets, only odd-numbered harmonics emerge. This distinction creates the characteristic tonal differences between these instrument families. The shape of the bore, cylindrical, conical, or flared, further sculpts the sound by emphasizing different harmonics. The trumpet's bright, brassy tone results from a predominantly cylindrical bore that flares at the bell, while the saxophone's sultry voice emerges from its conical bore. What's particularly enigmatic is how minuscule variations in bore shape create dramatic differences in timbre. The saxophone and clarinet, despite both being single-reed instruments, produce remarkably different sounds, primarily due to their bore geometries. Among wind instruments, one stands apart as truly otherworldly, the theremin. This instrument, invented in 1920 by Leon Theremin, is played without physical contact. Instead, the musician manipulates electromagnetic fields around two antennas, one controlling pitch and the other volume. The theremin operates through capacitance, the same principle used in touchscreens. As the player's hands approach the antennas, they become part of an electrical circuit, altering its resonant frequency. This frequency change is converted into an audio signal, creating the instrument's distinctive, ethereal wail. The theremin demonstrates how musical instruments need not be mechanical. They can exist in the electromagnetic domain, translating invisible fields into audible sound. It serves as a bridge between traditional acoustics and electronic music, hinting at the vast sonic possibilities beyond conventional mechanical vibrations. Percussion instruments reveal yet another dimension of acoustic physics. Unlike strings or air columns, percussion instruments typically involve vibrating membranes, plates, or bars, each with their own complex vibrational modes. When a drumhead is struck, it vibrates not in a simple pattern, but in complex modal patterns, concentric circles and diametric lines that create rich, inharmonic spectra. These patterns, first mapped by Ernst Chladni in the 18th century, using sand on vibrating plates, reveal the hidden geometry of sound. Particularly mesmerizing are instruments like singing bowls and gongs, whose vibrations evolve over time as energy transfers between different vibrational modes. Strike a large gong, and you'll hear not a single note but a sonic journey as the metal's vibrational energy shifts between different resonant patterns, creating that characteristic shimmer and wash of sound. Even more perplexing are instruments like the hang drum or handpan, whose complex dimpled geometry creates tuned areas that interact with each other through the metal, producing sounds that seem to defy their physical origins. The physics of bells represents one of the most mathematically complex areas of musical acoustics. Unlike many instruments, bells produce overtones that don't follow the harmonic series. Instead, their partials follow a proprietary pattern that gives each bell its distinctive character. This complexity extends to the casting process itself. Bell founders have long known that the precise shape of a bell determines its sound, but the mathematical relationships are so complex that for centuries, bell-making remained more art than science. Modern analysis has revealed how specific geometrical features correspond to particular partials. The thickness profile determines the minor third, the curvature influences the fifth, and so on. Yet even today, the finest bells emerge from a delicate dance between computer modeling and traditional craftsmanship, between science and intuition. As we venture into modern instruments, the boundary between acoustics and electronics blurs. Electronic instruments don't produce sound through mechanical vibrations, but through oscillating electrical circuits that are converted to sound waves by speakers. The theremin was just the beginning. Instruments like the Moog synthesizer generate sound through voltage-controlled oscillators that can produce waveforms impossible in the acoustic realm, perfect square waves, sawtooth patterns, and more. These instruments aren't bound by the constraints of physical resonators, but can create sounds limited only by mathematical possibility. Digital synthesis takes this further, using algorithms to generate or manipulate sound. Techniques like frequency modulation, granular synthesis, and physical modeling create soundscapes that have no acoustic counterpart, yet follow their own mathematical logic. What's particularly fascinating is how many electronic instruments mimic acoustic principles. Physical modeling synthesis, for instance, uses equations to simulate the behavior of vibrating strings or air columns, creating virtual instruments that respond like their physical counterparts while transcending their limitations. Recording technology represents another intersection of physics and music. Microphones convert sound pressure waves back into electrical signals, essentially reversing the process that speakers perform. But this transformation is never perfect. Each microphone has its own frequency response, directional sensitivity, and dynamic characteristics. The physics of microphone placement becomes an art form in itself. Placing a microphone at different positions relative to an instrument captures different aspects of its sound. Closer to a violin captures more bow noise and direct string sound, while further away captures more of the instrument's body resonance. Similarly, the acoustics of recording spaces, from legendary concert halls to purpose-built studios, shape the recorded sound through patterns of reflection, absorption, and diffraction. These acoustic properties can be measured and modeled, yet the finest recording engineers still rely on their ears as much as their measurement tools. At the frontier of musical acoustics lies a world of experimental instruments that challenge our understanding of sound production. Consider the hydrolophone, an instrument that uses water as its vibrating medium. As fingers interrupt jets of water, they create pressure oscillations that generate sound, creating an instrument that responds to touch in entirely novel ways. Or the sousaphone, a singing Tesla coil that modulates electrical arcs to create musical tones, literally playing with lightning. These plasma oscillations create sound waves directly in the air without a traditional vibrating body. The reactable transforms musical interaction through tangible interfaces, physical objects placed on an interactive surface control digital sound generation. Here, the physics is not in the sound production, but in the interface between performer and sound. These experimental instruments hint at vast unexplored territories in the physics of music, new relationships between energy, matter, and sound waiting to be discovered. They remind us that despite centuries of acoustical research, we've only begun to explore the possibilities of musical physics. As our exploration of musical physics concludes, we're left with a profound paradox. The more precisely we understand the mathematics and physics of music, the more its emotional impact remains a mystery. We can explain how a violin string vibrates, how resonance amplifies its sound, how overtones give it richness. Yet we cannot fully explain why these vibrations in air can bring tears to our eyes or send shivers down our spine. Perhaps this is the ultimate enigma of musical physics, that such profound emotional responses can emerge from mathematical relationships and pressure waves. The instruments we've explored today are not merely devices for producing sound. They are interfaces between the objective world of physics and the subjective realm of human experience. In this way, musical instruments represent one of humanity's most remarkable achievements, the transformation of mathematical principles into emotional expression, of physical law into artistic statement. As you listen to music in the days ahead, I invite you to hear it with new ears, to perceive not just melodies and rhythms, but the invisible forces that create them. Listen for the harmonic series in a plucked string, for the modal vibrations in a struck drum, for the resonance patterns in a flute. In our next lecture, we'll explore another fascinating intersection of science and art, the mathematics in art and architecture. Until then, may you find wonder in the physics that surrounds you, in music and beyond.